In this session, we'll have a brief look at the pinout of 80386 to the effect as to what are the signals which are available with 80386. These signals actually make more sense when we start using them for different purposes, which we will do as we go through the session. So this is the pinout of 80386. It's quite similar to 80286 or 8086. They have a lot of common signals. So first let's start with the main inputs to 80286. There is a clock input, reset, ready and bus size 16. This clock is clock 2 because if 80386 is going to work at 16 megahertz, this clock has to be 32 megahertz. So if you want it to work at 15 megahertz, it follows that this clock 2 must be 30 megahertz. So 80386 actually works at half the frequency of clock 2. That is why the term clock 2, you're giving a frequency twice the frequency at which the processor will be working. The reset signal, same, it's used for resetting 80386. Ready again has the same purpose. It's used for indicating whether wait states must be introduced or not. So if it is low, wait states are introduced. If it is high, it continues at the normal speed of operation. Now bus 16 is a unique signal in the sense that if this signal is connected to ground, only the data lines D0 to D15 will be active. The size of the data bus becomes 16 bits. When bus size 16 is low, the size of the data bus becomes 16 bits. That is, you will have only the data lines D0 to D15 available. In this case, 80386 is then working like its equivalent, which is 80386SX. There are different versions of 80386 available. One of the versions is 80386SX. In 80386XS, all the internal architecture remains the same. The difference is going to be the data bus will be 16 bits D0 to D15. Now, if I make the bus size 16 signal low here, this behaves like 80386SX. You'll only have data lines D0 to D15. Data lines D16 to D31 are not going to be available. But if you make this high, then in this case, it means that all 32 data lines D0 to D31 will be available. There is another variant of 80386 which is called as 80386EX. So 80386EX, the difference is going to be that in 80386EX you have one more signal available which is called as the bus size 8 signal. The bus size 8 signal allows you to control the data bus to be 8 bits, 16 bits or 32 bits. So that is another version of 80386 available, which is 80386SX. EX. In 80386EX, you can have either a 8-bit data bus, you can have a 16-bit data bus or you can have a 32-bit data bus. 80386SX will only allow you to have a 16-bit data bus. 80386 will allow you to have either a 16-bit data bus or a 32-bit data bus. So these are the different versions of 80386 available. Normally when we are talking about 80386, this is the version that we are referring to, which allows you to have 16-bit or 32-bit. 80386SX, only 16 bits. 80386EX, 8 bits, 16 bits or 32 bits. That's the difference between these three versions. So let's get back to the pinout of 80386 and have a look at the other signals which are available with 80386. That's other than the clock, reset and ready. Now similar to 8086 and 80286, 80386 also requires a clock generator. The clock generator used here in case of 8086 it was 8284. 80286 it was 82284. In case of 80386, it's 82384. So 82384 is the clock generator which is used along with 80386. 82384. Now let's look at the other signals. There is going to be the address lines which are available. The address lines, as you can see here, are going to be only A2 to A31. A0 and A1 are not generated by 80386. Instead, 80386 generates four signals which are called as bank enable signal. Bank enable 0, bank enable 1, bank enable 2, bank enable 3. The reason is the data bus can be treated as 4, D0 to D7, D8 to D15 and D16 to D23, D24 to D31. So you have four parts of your data bus. Your data bus 32 bits is divided into 8 data buses. Associated with each of these 8 data lines is going to be a bus enable signal. So bus enable signal 0 means that data transfer will take place on the data lines which are going to be D0 to D7. With bus enable 1, it means that data transfer is taking place from D8 to D15. Bus enable 2, it means data transfer is taking place from D16 to D23. And when data transfer takes place on the highest byte, which is D24 to D31, in that case bus enable 3 is going to be active. Now if you're doing a 32-bit data transfer, all four of them will be active. If you're doing a 16-bit data transfer on D0 to D16, then in that case what is going to be accessible is D0 to D15. Bus enable 0, bus enable 1 will be active. If you're doing data transfer on D16 to D31, a 16-bit data transfer, BE2 and BE3 are going to be active. So you don't have address lines A0 and A1. Instead you have 4 bus enable signals: BE0 associated with D0 to D7, BE1 associated with D8 to D15, BE2 associated with D16 to D23, and BE3 associated with a higher order data bus which is going to be D24 to D31. Okay, so these are the address and data. Again, if you note, it is demultiplexed address and data lines. So the address lines of 80286 as well as 80386 both are going to be demultiplexed. Let's look at the control signals. The control signals which are available are memory/IO bar, same as in 8086 or 80286, read and write. They are combined together. If read signal is going to be low, then it is a read operation. If the signal is going to be high, it's a write operation. There is one more signal which is called as D/C, data/code. D/C is data/code. Now, if this signal is going to be high, it means that some kind of data transfer is taking place. It might be data from memory, data return into memory, data read from an input device, data return into an output device, but data is going to be used. If this signal is low, essentially it means that some kind of control transfer is taking place, meaning that a interrupt acknowledge bus cycle might be taking place. So if this is low, it might be an interrupt acknowledge bus cycle. So data/control, data being high, control whenever it is going to be low. Now these three signals are going to be used for generating our 4 or 5 main bus cycles. The 5 main bus cycles, if you remember, are going to be memory read, where you will get the memory and the read signal. You will have memory write. Then there is going to be IO read. There is IO write. And the fourth type of machine cycle is going to be interrupt acknowledge. So in interrupt acknowledge bus cycle, D/C signal will be made low. Now again, this is not in the format that you are expecting. So it means there will be an external bus controller. With 8086 we had 8288. With 80286 we had 82288. In case of 80386, you have an equivalent bus controller available, and this bus controller will be generating the memory read, the IO read, memory write, IO write, and the interrupt acknowledge signals. So these three signals will be given as input to the bus controller, and the bus controller will be generating these 5 signals. Now let's look at the other 2 signals, which are ADS bar and NA bar. ADS bar is address strobe. This signal is active whenever a valid address is going to be generated. NA bar is an input to 80386 asking it to generate the next address. Now, how do these two work together? Right now they may not make much of a sense. ADS bar, we know that is going to be address strobe. Valid address, the signal is active. NA bar is an input. It is given whenever 80386 is supposed to generate the next address. But together they are used for what is called as bus pipelining. We'll talk about bus pipelining towards the end of this module. Then you will understand how does ADS bar and NA bar work together to implement a process of bus pipelining. So these are going to be the control signals. Now let's look at the other signals. With the coprocessor, of course, 80386 also has a coprocessor. Obviously that coprocessor is 80387. So with that we have three lines: processor extension request. This is given by the coprocessor whenever it wants to do a bus cycle in order to fetch the data. As you can see, there is no acknowledge here. A request means automatically the bus will be given to the coprocessor. The coprocessor will then fetch data, and as long as the coprocessor is busy, the busy signal is going to be low. If there is any error with the coprocessor, this signal is going to be activated. Once the processor has completed its bus cycle, then automatically PE request will be inactivated. So there is no acknowledge, there is only request. In case of 80286, there was request, acknowledge, busy and error. Here there is only a request. A request is given by 80387 saying that it wants the bus. Bus is granted. Without the acknowledge, the 80387 will take over. It will complete its bus operation. Once it's completed it, it will make bus request inactive, or it makes it high, indicating that it has completed the bus transfer. Now those are the processor extension request signals. The other signals are interrupt. Again, NMI and INTR, no difference between the NMI and INTR of 80286 and 80386, it remains the same. Then there is the DMA signal. It's same right from 8086, hold and hold acknowledge. There is a lock input which we have seen earlier with 80286 also. The lock input is given by it's an output, it should not be an input signal. Lock is going to be an output from 80386. The function of the lock signal is 80386 is doing some bus cycle, and as long as these bus cycles are taking place, no other external bus master must try to take over the bus. So when the lock signal is made low, automatically it indicates that 80386 is not ready to hand over the bus. It locks the bus and keeps it with itself. That is the purpose of the lock signal. The lock signal is always associated, as we saw in case of 80286, with the lock in prefix. An instruction can be given a lock prefix, and as long as that instruction is executing, no other processor can take over the bus, or no other bus master can take over the bus. Lock is the prefix, and on the execution of the lock prefix, automatically the bus is going to be locked. It's not going to be available to the external processors which are present in the system. So this is the pinout of 80386, demultiplexed address and data lines. We don't have address lines A0 to A1. Instead, we have bus enable 0 to bus enable 3. We have three main control signals: memory/IO bar, read bar/write, and D/C bar. We have two signals which are used with pipelining: ADS bar and NA. This is bus pipelining, not the internal pipelining of 80386. We have a clock signal whose frequency will always be twice the frequency at which 80386 is working. The normal reset and ready. Other than that, the bus size signal, which decides the size of the data bus, whether it is going to be 16 bits or whether it is 32 bits. We also have a series of signals which are for processor extension or for coprocessors. Two signals associated with interrupt which were similar from 8086, the DMA signal and the lock signal, which prevents any other device from taking over the bus of 80386. So we'll stop with this in this session.